Operation of a diode and light emission. For a diode, we consider a semiconductor with selective contacts so that we can modify the initial position of the Fermi levels by applying a voltage. And there are two ways to apply the voltage. We can increase the concentration of minority carrier, and this is going to create a large number of minority carriers by injection, and it will induce recombination and probably luminescence, so that here the current will increase exponentially with the voltage. In the other direction, we decrease the population of minority carriers, so nothing happens. But we always have in the background the thermal generation of carriers from the surrounding black body radiation. So in the situation of voltage zero, there is an equilibrium of these two, of the current associated to generation, J naught, and the current associated to recombination. So this J naught will always be the same because the generation by the dark surrounding is not changing. So we always have this J naught in the diode equation. This J naught is the reverse saturation current, and it's a constant related to recombination. From this consideration, we can construct the diode equation, because in the dark, we have the reverse saturation current associated to charge generation by black body radiation and equilibrated by a recombination current, and both are the same. But we can modify the recombination current if we increase the voltage by applying a bias to the left contact that will raise the Fermi level of electrons. So this will induce a strong recombination current, and the current will grow exponentially. So the recombination current as a function of voltage will be J naught, which is the reverse saturation current, which is the essential recombination parameter. And as we increase the Fermi level, increase the population of electrons, this will increase exponentially, like QV over the Boltzmann constant T, temperature. And we add another parameter, which is the ideality factor. Which is M, and describes how the recombination increases with the voltage. So we have two currents, the generation J naught and the recombination, and they add to the injection current. So this J is the external current in the diode, the current that we can inject. And finally, the equation for the diode is J0 multiplied by 2 terms, an exponential -1. So that when the voltage increases, we have an exponential growth of the current. If the voltage increases in the other direction, like negative here, then this term will disappear, and we have only the constant current associated to carrier generation in the dark. And this is the reason why this parameter is called the saturation current. When the voltage is zero, we are in equilibrium of the two currents, and it's exactly zero at the origin. So this is the characteristic of the diode that generates current by recombination only in one direction of applied voltage, and in the other one, it gives a constant current. Of course, this we can change by illumination. If we generate carriers by light, we have another factor that is then the operation of the solar cell. So let us clarify the direction of the voltage, gets this special name. Forward is a negative potential applied to the electron selective contact, or a positive potential applied to the hole selective contact, so that this will separate the Fermi levels in the direction of creating more carriers. The reverse voltage is the contrary situation, is a positive potential applied to the electron selecting contact, which is moving in the other direction, the Fermi level of the electrons. So that the forward voltage increases the number of carriers, while the reverse voltage causes a situation in which no carriers are injected, so only the carriers generated in the dark are extracted. We have defined the diode by two parameters, J naught. This is the amount of recombination in the dark when the diode is in equilibrium, that is expanded by exponentially by the forward voltage. And we can see that the current increases according to J naught. So if J naught is large, there will be much more forward current, and also the same in reverse. Here it is defined, the constant current defined by the J naught. And the diode ideality factor indicates how rapid is the exponential rise. So it can be m equals 1, 2, etc. This is the typical values depending on recombination mechanism in the semiconductor. There are different types of diodes depending on how the mechanism for injection is realized. Here, this is a majority carrier diode because it is a Schottky barrier. When we apply a forward bias, that is a negative voltage to the electron selective contact, the Fermi level rises. The step of the Fermi levels is at the other interface, and we are decreasing the barrier so that we have more injection of electrons and the current increases in the direction of forward bias. Another type is the minority carrier. Now here we do the same as before, apply negative voltage to the electron selective contact, which is decreasing the barrier. But then instead of injection here, what we obtain is better injection of holes. Therefore, the holes that are minority carriers here are injected, and we have the recombination inside the semiconductor. This diagram summarizes the situation. This is a p-type semiconductor now, where electrons are minorities. The first diagram is in equilibrium with the two currents compensated. And now we apply a forward bias, negative to the electron selective contact, and we inject more electrons, and these are recombining. If we apply a reverse bias, which is positive to the electron selective contact, we are going to increase polarization. But this doesn't make any significant effect because no carriers are injected and we only can extract the thermal generation. This is a diode by a semiconductor electrolyte junction. And here we have an increase of the Fermi levels of the majority carriers. So we will have more injection into the electrolyte, and then the current increases. So this is also a diode. This type of diode can then be applied in a water splitting cell, in which now there will be the electrons flowing into the solution in one electrode, and the holes making an oxidation reaction, probably water splitting at the other one. By having a semiconductor in the diode configuration, we can apply a forward bias and then induce intense recombination, and the semiconductor will emit light because these electron hole pairs are going to be converted into photons, so that this is a light emitting diode in which the light emission will increase exponentially with the voltage. We can also obtain photoluminescence by applying a high energy stimulus of the semiconductor. This is representing a collection of different types of quantum dots. By the quantization effect, the light emission is going to move, and we can stimulate the light emission by applying a light of energy significantly larger than the bandgap, and then the semiconductor will emit light. We can see that the light is emitted at the edge of the absorption spectrum. So either by illumination or by application of a voltage, we create excess carriers in the semiconductor, and this is going to produce light emission, but the recombination might be radiative or maybe non-radiative. For example, if there are traps in the middle of the bandgap, or if there are surface defects, then we can have a significant extent of non-radiative recombination, in which the recombination is converted into heat, not into light. So that basically we have two mechanisms. The radiative recombination gives light, and this is the essential recombination in a semiconductor. And the non-radiative recombination produces heat, and it can be suppressed by removing recombination centers.